Assalamu alaikum, my name is Aisha Majid. For my part of the code, first of all, I'm importing some libraries to improve the functionality of my code. First is immutils, which is a Python package for simplifying OpenCV functions. Next is CV2, which is a powerful library for image processing. NumPy as NP is a numerical computing library again. And matplotlib.pyplot. SPLT is for visualizing the images. Next is the OS library. This is for directory management. And shuttle is for copying files from sources to destinations. Then we have scalearn utils.shuffle, which is basically to shuffle all of the images. Like in our case, we have two types of images, one containing the tumors and the other images that do not contain the tumors. So we are basically going to shuffle these images, tumors and non-tumorous ones. In the first segment, we are going to be working on data processing, converting blue, green, red to grayscale images, like BGR images to grayscale images. Gaussian, we're going to apply Gaussian blur, threshold, erosion, dilation, and we're going to find the contours. So in the first function, which is the crop brain tumor, we are going to import an image in which we are going to detect the brain tumor, and we are going to perform a cropping mechanism just so we can get the brain tumor and not the whole scan. And the second is the plot, which is set to false as a default, and which is basically a Boolean flag to decide if the original and the cropped images should be displayed. In the next function, which is where we are going to convert the BGR image into the grayscale image, we are using again a OpenCV2 function, which is a powerful image processing library. So the function is CVT color, so which means we are going to convert the color from a blue, green, red format to a grayscale, which is going to be a black and white format. After this, the gray image will only have brightness values, not colors, and its pixels are going to range from 0 to 255. Next is our Gaussian blur function. Gaussian blur is basically applied to the grayscale image, the BGR image we just converted into grayscale. The purpose is to reduce noise and smooth the image, basically helps in better contour detection by removing high frequency noise. Which is a Gaussian blur is again a CV2 library function, where we have imported and presented our grayscale image and the kernel size and a standard deviation value. So the gray is basically the grayscale image we just converted, and 5,5 is the kernel size, 5 pixels wide and 5 pixels tall, and 0 is the standard deviation value, which is calculated automatically. So the next function is where we are applying the threshold. So threshold is basically, so it's a long story. So the first image we had, like the image we started off with, was a BGR image, means a colored image. BGR, blue, green, and red. So the pixel for blue, let's suppose it's 120, and for green it is 200, and for our red it is 80. So when we convert it into grayscale, it can give a particular number ranging from 0 to 255. In this case, we can suppose it is 145. So this is a grayscale image converted from BGR. And why do we actually apply threshold? Because we do not know on which pixel to decide, from the blue or the green or the red. So we first convert it into grayscale and then we threshold it, meaning we just give it a magic number, let's say 45. So all of the pixels above 45 are going to be white, and below 45 they're going to be black. So it is easy for the computer. So in this function, thres is basically where we are going to be stored the threshold image. Here we are passing our grayscale image, our magic number, and the maximum limit, which is 255. It basically converts the blurred image into a binary image. So the threshold value is 45, maximum value is 255, which is also white. And pixels with the values above 45 are turned 255, and the pixels with the values below 45 are turned 0. Like when I explained earlier that our BGR colors are 120, 280, which are then collectively converted into a grayscale image, giving a number 145. So 145 is a number above 45, so it is going to be converted to 255 directly, which is basically thresholding, and it is turned white. Our next function is erode, which is basically erosion, and it is applied to the threshold image we just modified. It shrinks white areas and removes small white noise, and it is going to iterate for 2 times in this case, which means the effect is applied 2 times for a stronger effect. So we are just using a CV2 erode function, which is again from an OpenCV library, and we are passing in our threshold image. None is basically the default kernel size, 3x3 width and height, and iterations are 2, which means the effect is going to be 2 times for the erosion. Next, we are using again an OpenCV2 library function, which is dilate, and dilated is applied next. It expands the white region, strengthens the shape of the detected objects. We are passing our threshold image, the none, which is basically the kernel size, 3x3 width and height, and iterations are true for a 2 times more stronger effect for dilation on our object. Our next function is again an OpenCV2 function, which is find contours. So contours are basically x and y coordinate points, which basically make up the base to draw a bounding box around our tumor. So this function is basically, all of the functionality of this function is basically stored into a variable sense. So here we are passing our threshold image copy and 2 more functions, which is again CV2 OpenCV2 functions, which is retter external. And in the OpenCV2 retter external function, only the outermost contours are detected, and in the chain approx simple function, only it compresses the horizontal, vertical, and diagonal lines, whatever lines they are of the type. They just extract the x and y points, which means the starting and the ending points, and it is done only to save the memory. Then our next function is immutils.grab _contours. It is used for compatibility with OpenCV versions, because some of the OpenCV versions return different values. Like for OpenCV version 4, 3 values are returned, which is the image, contours, and the hierarchy, and for OpenCV 2 or 3, 2 values are returned, contours and hierarchy. So this function basically normalizes and makes everything consistent and returns the same number of values, so there are no conflicts. Well, next we are going to find the largest contour, all of the x and y coordinate points from all of the x and y coordinate points. We are going to find the largest contour. For that, we are using the max function with cv2.contour area as the key, and the max function is going to give us the maximum calculated area value for the particular contour, which we are going to represent as the tumor region. cv2.contour area is a special OpenCV function which calculates the area for each contour. This means how much space the shape takes in the image, and the maximum shape it's going to take, the maximum space is going to be directed as the tumor. After that, the largest contour is stored in the variable c. So in the next segment, we are going to find the extreme points. Extreme points are the furthest points on a shape contour in each direction. So x to left, which is basically the leftmost point, x to right is the rightmost, x top is the topmost, and the x bot is the bottommost. All of these points are going to make the base for our bounding box. These 4 points help us create a bounding box around the object, which is basically our tumor. A bounding box is a rectangle that perfectly surrounds an object. So if we take our first function, which is the x to left, and we are using a tuple function which basically returns only the x and y coordinate values after the computation and all, and the argmin function basically points to the smallest value on the x-axis, which is also going to be our leftmost value. Okay, after that, the same applies for the x to right, but instead it finds the largest x value, which is going to be our rightmost point, and that is going to be detected and stored by the argmax function. All right, then the x-top function, again that tuple function is used to return the x and y coordinates, and the argmin function over here finds the smallest y value, which is going to be our topmost value. And for the x-bot, our argument max is going to find the largest y value, which is going to be our bottommost point. And once all of these points are decided, we are going to form a bounding box around the tumor using these 4 points. So after that, we are going to crop our tumor region, and it is going to be all stored in the new image. So in the next segment, we are going to work on plotting. So the first line of course says if plot, which basically denotes if plot is equal to true, it is passed, and the function will create a figure with 2 subplots. On the left side, we are going to represent the original image, and on the right side, we are going to represent the cropped image, the tumor region basically from that image. This helps visualize the cropping process. So basically in the subplot, you see 3 arguments, 1, 2, and 1. So the first one is the number of rows, 2 is the number of columns, and the 1 on the rightmost side is the box, and it is counting left to right, top to bottom. Basically it is representing that we are in the first box of the subplot, and it represents our original image and not the cropped one. And after that, we are going to have the plt.subplot, the other function, and it is going to draw the second box because they're saying that we are in the second box from the 1 and 2. It is saying 2, so we are in the second slot right here, and in the second slot we have our cropped image. Our only tumor region is residing in there. This is basically showing the before and after. We cropped the image, and from the entire scan it is just showing the 2 images side by side for visual representation, and at the end we return the new image, the cropped image, which is our tumor region. It is returned. Next, we are going to define the folders containing images. So we have 2 folders, folder 1 and folder 2, where folder 1 contains augmented data no, which represents the augmented data containing no tumor, and folder 2 represents the augmented data containing the tumor, which is the yes path. So we set 2 variables, folder 1 and folder 2, that store the paths to 2 directories. These directories presumably contain images classified as no for no tumor and yes for the tumor being present in the images. Okay, so then we are going to list all the files in folder 1. The os.list dir is basically the folder 1, contains the folder 1. This function returns a list of all file names in the directory augmented data no, and the for loop will iterate over each file name, like for example image1.jpg or scan23.png, etc. all of the files in the folder 1. Then we are going to read each image file from the folder 1, and the cv2.imread function loads an image from disk into the memory. It basically concatenates the folder path and the file name to get the full file path, for example augmented data no slash image1.jpg. Where we basically call the crop brain tumor function, which we just described above on the particular image. So we call a custom function, which is a crop brain tumor on the loaded image, which is described above. This function likely crops the image to focus on the brain tumor area. The second argument false is a parameter to the function probably controlling some aspect of cropping or processing. At last, we overwrite the original image file with the cropped image. cv2.imwrite saves the processed image back to disk, overwriting the original image in the folder. This means the original image file is replaced with the cropped version, and we repeat the same steps for all the files in folder 2, which contains the augmented data yes directory. Next off, we are going to be working on image loading. So we are using a function load data. It is having 2 parameters, directory list and image size. Directory list is a list of directories or folders where images are stored, and the image size is a tuple containing the width and height specifying the target size for the images. Then we have 2 arrays. X is an empty list to store the processed images, the feature data, and the Y is an empty list to store the corresponding labels for the feature data, the target data basically. Next, we extract the image dimensions. Image width comma image height is equals to image size. We are basically unpacking the image size tuple into 2 variables, that is image width and height. Then we loop through directories and files. The outer loop iterates through each directory in the list directory list, and the inner loop iterates through each file or image in the current directory. Then we read and process each image. So this line image is equals to cv2.imread basically reads the image from the current directory using OpenCV's function cv2.imread, and the full file path is created using directory plus the slash plus the file name. So it is basically going to give the entire path for the particular image. Then we crop the image using the custom crop function, where we given our image as an argument and the plot where the false value, a flag, is set as default. Then we use the cv2.resize function and we apply it on our image, which basically resizes the cropped image to the specified size, where our desize uses the two variables, our two parameters, image width and image height, and it sets the target width and height. And the cv2.intercubic function uses cubic interpolation, which provides high quality resizing. Then we normalize image values by dividing each image value by 255. It then basically scales all of the pixel values from 0 to 1, and it is basically for a better understanding of the machine. Then we append the image data to list, which is x.append, and we pass in the image. So this basically adds all of the images with its parameters in the X array. Next, we assign the labels, like if directory is -3 is equals to yes, which means we are assigning a label based on the directory name. If the directory name ends with yes, it means the image contains a tumor, so the label is 1, and otherwise the label is 0 and the image is not containing the tumor, which is indicating no tumor. After that, we are converting the list to the numpy arrays. X is equals to np.array x and y is equals to np.array y, which converts the list of images x and labels y to numpy arrays for efficient computation. After that, we are shuffling the data, like the tumorous and the non-tumorous images. This basically shuffle function randomly shuffles the images and labels using the scalar.utils.shuffle. This prevents any ordering bias in the data. Lastly, we are going to print out information using the print functions. A number of examples, the total number of images basically are the shape of the x, which is the image data, and the shape of y, which are the labels for the corresponding target data. After that, we are going to return the data and the labels. So we are going to just simply return x, y. The function returns two numpy arrays. X is the array of the processed image data, and the y is the array of the corresponding labels for the target image data. And we're going to set our augmented data path. So the augmented data path is the base directory where the augmented images are stored, and augmented_yes is the full path to the directory containing the images with the brain tumors, which was augmented_data/yes, and same as for the augmented_no is the full path to the directory containing images without the brain tumors, which was augmented_data/no. Next, we are defining the target image size. Image width, image height is equal to 240 to 240. Says the target dimensions for resizing the images. Basically, like the image width is going to be 240 pixels. That is going to be the width, and the image height is also going to be 240 pixels. Then we are going to load and process the images with the load data function. So with the load data function, we are storing it in our two arrays, the image and their corresponding labels, where we give the directories augmented yes and augmented no, and their respective image size in respect of width and height, which is 240 pixels we just decided on. So it's going to give an example output is going to be something like 2063 images as a whole, and their size is going to be 240 by 240 width and height. And Y shape is also going to be 2063 because they are the corresponding labels for all of the images. Next, we need to list our images into a grid. We are going to list all of the images in a format of a grid. So for that, we are going to use a plot sample images function where we are importing our X and Y shapes and a limit of n is equals to 50. This function basically has the X parameter as a numpy array containing the images, which is going to have the shape, num samples, the total images, their width and height in pixels, which was 240, and the channels, which is the BGR channel. And for the Y, we are going to have only the num samples, which are going to be the total number of images. Their labels basically we are going to use for the total images. And n is the number of images to display for each class. Default is 50. Then we loop through the two classes 0 and 1 for label in 0, 1 for loop that iterates over two labels. 0 is indicating that we do not have a tumor, and yes is for 1 indicates that we do have a tumor. Then we are filtering the images by label. We use np.argvar function to find the indices of all images that match the current label. If label is equals to 0, it gets all images labeled 0, and if the label is 1, it gets all images labeled 1. These filtered images are stored in images variable. After that, we are selecting the first n images. N images is equals to images : n. It selects the first n images from the filtered list. If n is 50, it selects the first 50 images of the current label, 0 or 1. Now for plotting, we are going to calculate our rows and columns. So we have to list 50 images. So for that, we are going to give the column values. Column n is equals to 10, and for rows, we are going to divide it by the total number of we are going to divide the total number of images, which is by default 50, by the number of columns, which is 10. So 50 by 10, we get 5, and that is going to be our number of rows. So the grid of 10 columns and 4 rows is going to give us 50 images at a time to display. Then we initialize the plotting figure, the actual individual plotting figure, using the plt.figure function. It is using fixed size, where we have fixed size 20, 10. It creates a new figure using matplotlb, which is a library we use for resizing. It sets the figure size to 10 inches. This makes the grid of images large and clear. Next, we loop through and plot each image. For that, we initialize a counter I for the subplot position, and the next line iterates through the first n images of the current label. After that, we create a subplot at position I, where rows underscore n is the number of rows and columns underscore n are the number of columns, and I is the current position. plt.imshowImage 0 displays the image in the subplot, and the 0 is used because the image is wrapped in an extra dimension by np.argvar function. So after that, the plt.tickparms is a function. This hides all the access ticks and labels. No tick marks top, bottom, or left or right. We do not have any tick marks, so it is not clear. No tick labels, label bottom or top, left, right, anything like that. Then the I increments and moves to the next subplot. After that, we are adding a title to the plot, label to str. We are using a lambda label. Yes, if the label is 1, else no. Defines a lambda function to convert labels into text. 1 becomes yes and 0 becomes no. And it sets the main title of the figure. For label 0, brain tumor does not exist, and for label 1, brain tumor does exist. Lastly, we are just displaying the plot function plt.show, and it renders and displays the figure with the grid of images, 50 images in total at a time. Next, we are going to check if our directory exists for tumors and non-tumors. os.path.isDir tumors and non-tumors. This basically checks if a directory named tumors and non-tumors already exist. Return true if the directory exists and false if it does not. And if not, the not operator inverts the result. If the directory does not exist and if it is false, the condition is met. After that, we are setting the directory name base dir. Tumors and non-tumors defines is basically we are defining a variable named base dir, and we are assigning it the string tumors and non-tumors. Next we're going to create the directory os.mkdir. We're going to create that base directory, and if the directory already exists, this line is skipped because of the if condition. After that, we are supposed to create a training directory, and we are going to repeat the exact same steps we did for the tumors and non-tumors directory. If the training directory, we are first going to check if the tumors and non-tumors /train exists, which means the training directory for tumors and non-tumors exists. Then the condition is not met, and if it does not exist, the code inside the if block runs. After that, in the same way, we are going to create our testing directory and our validating directory. We are doing this just to train, test, and validate our data and our mechanism of detecting brain tumors. And the same thing is repeated for our non-tumors part. We do the same thing. We create the directories train, test, and validate for the non-tumors as well, in the same way we did for the tumors. After that, we're going to set the path for the tumors dataset. os.path.join combines the base directory augmented data with the subdirectory yes / this is the path where the tumors infected images are stored. os.path.join we use instead of a direct string. It ensures that the path is correctly constructed for any operating system. Again, for Windows it's different, and for Linux or Mac it is different, and this makes your code more portable. Again, we are going to set the path for the non-tumors dataset in the same way. This is the path where the non-tumors or healthy images are stored, which do not contain the tumor. Lastly, we're going to list all of the files in the tumors directory. The files are basically, we are going to first retrieve a list of all the files names in the directory augmented data yes. The list files will contain the names of all images, like the image1.jpg, image2.jpg. After that, we're going to select a subset of files for the first 759 images. We're basically breaking it down into segments for more better processing. We are first going to create an empty list of f names to store the selected file images. Then we use a for loop to iterate from 0 to 759 images in total, and append the first 759 file names from files to f names, the list we just created. Then we copy the selected files to the training directory from source. We give the source path and we copy it basically into the destination path using the shuttle.copyFile function, and we give in the source and the destination paths for it, so it copies from the source to the destination. And in case the destination file already exists, it will overwrite the destination path. After that, we're going to work in the same way from the images above 759 onwards to 922. We're going to do the exact same thing. We're going to load in total 163 images. Then we copy the selected files to the test directory. Again, for copying them into this test directory, we use a for loop which iterates over each file name in f names, and we give in the source path and the destination. And using the shuttle copy file function, we basically copy the source path from the source to the destination path address. After that, we are again going to list all files in the tumors directory. From this time, we're going to do it from the range 922 onwards to 184, and in total we are going to copy 162 images. Okay, we're going to copy 162 images in total into the validation directory. And the exact same process we are going to repeat for the non-tumors files we have. First, we start off from the range of 0 to 686, and then from 686 we go to 833, and from 833 we go to 979, and all of the images are copied till the validation directory is reached.